Good evening. Tonight I want to review our discussion in class today of the evaluation of limits. There are basically 9 limit definitions. However, if you don't want to call it 9, you could say, well, this is 9, 10, 11, and 12. So this would look like 9, 10, 11, and 12 as far as definitions. But they fall in 9 categories, and I want you to kind of take a look at what I'm talking about. Here, this bunch of 3, we always have x approaching a number. Now, when we say x approaches C, C is the domain and L is the range. So let's kind of write this in here, that C is going to be the domain and L is going to be the range. So when we're talking about limits and we're talking about graphically, the limit of something is the y value. The big word by the time you got to the 7th grade was calling the y value the range and the x value the domain. Notice I have x approaching C each time in this category, and I have an actual number, I have infinity, or I have negative infinity. Now, you know what graphs look like this. You're going to find when you do the graphical exercises today that you did in class or tonight for homework, that when you had x approaching C, C was the domain, and you had a y value here called C comma L, and this approached it, and then it kept on going. So it approached it from the right side as well as the left side. The function could be continuous, and you also learned in working today, it could be discontinuous. So if you have a solid dot, it would be continuous, but if that dot would be open, it would be discontinuous. Now, I don't want you to get too involved in wondering why this happens. You can't possibly understand why the limit of f of x as x approaches C as L would be that there'd be an open circle at C comma L, because it would seem weird to you. How is it going to get there? I'm saying it's approaching C. I want it is L. I want it solid, Miss Mallory. Well, guess what? It doesn't have to be solid because of a nice, lovely proof in mathematics. We will get to that. See you tomorrow. Okay. The same case of x approaching a number, we're going to infinity. Common case of that is all the beautiful graphs that you had when you were little. And you had x approaches C. On both sides, you would come up to infinity. That means the right side of C, C to the left side of C. In the same aspect, we could approach C and we could go down to negative infinity on the right as well as on the left. Now, this 3 cases, x approaches C. Notice in case 4, 5, and 6, I have x approaching infinity. And again, I want to get L, infinity, and negative infinity as my range options. Domain remains the same, range options. Now think about what this has to look like. When you're talking about the limit of f of x as x goes to infinity as L, that means you're going to flatten out around a horizontal asymptote called y equals L. Now we're going to infinity. Well, look, our graph can just play around all it wants to do and go da-da-da-da-da-da-da-da-da, but finally it's going to play out. But in this case, when we say x approaches infinity and y is infinity, that just means we have an increasing function. And if we say here, as x goes to infinity, y goes to negative infinity, that means that as x gets bigger, y gets smaller, therefore our function is decreasing. Now, you have a very similar interpretation of L, infinity, and negative infinity when x is approaching negative infinity, as you heard today in class. Let's stop for a minute and pause. What we talked about today in class was setting up a lot of beautiful graphs to discuss the value as of y as x went to a number and our x went to infinity. The first case scenario that you did was by charts and tables. And what you did is you took your graphing calculator out and you were on page 22 of your handout, and you took values to see what would actually happen as x approached a number, and it got smaller and smaller to do. That exercise you should do. What was interesting was examples 1 and 2 at the bottom of page 22. Please note that in examples 1 and 2, your function is discontinuous. It is a piece function, and you had to consider what happens. This is called basically one-sided limits as x approached 1 from the right. Well, if you notice, x is approaching 1 to the right, the y value is going to be 2. But as the limit of f of x, as x approached 1 to the left, the y value was what? Yes, 1. Because what we looked at is when x was 1 coming in this way, we had a solid circle at the point 1, 2. So as x approached 1, the y value was 2. But as x approached 1 from the other side, this side, the value was 1. Now you're going to say, okay, does this limit exist? The limit existence theorem specifically says for a limit to exist, the limit of f of x as x approaches c to the right is equal to the limit of f of x as x approaches c to the left is equal to L. So in this case, the limit would not exist. However, if you would ask me what is the value of f of 1, I would say it's actually the number what? 2, not 1, because this is a beautiful solid circle. You should now be able to do example 2 on your own. Turn your page, the same questions are asked, and then we get to a very delightful exercise. If I can change the page, come on page, let's change. And it has to do with infinity. In this graph, I'm now on page, and I have to get used to this. Is my first recording. I have to really get used to using this pen. Maybe I will, maybe I won't. We have a vertical asymptote at x equals -2. Of course, this is the x-axis, this is the y-axis. And you have it coming up here and coming up here. So the limit as x approaches -2 from the right side is positive infinity for f of x, and the limit of f of x as x approaches -2 from the left side is infinity. You're going to say Does the limit exist? Ooh, what is an intelligent question like that? Coming around on the very first night of school. Well, we can philosophize here. If I formally define definitions 2 and 3 of limits to say that the limit of f of x as x approaches c to the right is infinity, and the limit of f of x as x approaches c to the left is infinity, then the limit of f of x as x approaches c would be infinity, and infinity, as crazy as it seems, I understand that you desperately want to put the initials D and E on here, but alas, no. Because on both sides of this vertical asymptote, at C, we approach infinity. Okay, let's see what other fun we have in that homework. Much repetitiveness. In example number 12, oh, it's a lovely graph here. You have a lovely graph. You're going to find out that example 12 is a very big highlight of something you're going to learn in sections 1.2. You have an oscillating function that all of a sudden oscillates on the both sides. And when it comes at x equals 0, you have the point 0, 1, and it's a solid point, and it does exist. So it may oscillate, and we can't determine the y value on the right side. We can't determine the y value on the left side. But if I say what is the limit of f of x as x approaches 0 is 1, and we are going to find a particular function that does that. And there are 6 special limits, and we will investigate them. That it's a real pretty set of homework, the special limits. I don't want to get into it tonight, but the proof of several of these are very, very complicated. With BC and any AB student that wants it, I will be more than happy to spend time on these by the squeeze theorem. For all those that want it, however, in AB, I will provide the proof. Then we'll come along to chapter 2, and that 3-page proof that you saw for those special limits, all 6 of them, ends up to be 1 line, because by 3 weeks from now, we really get smart. Okay, then we get on page 25, as well as 26, and we're reviewing the concept and the thought of approaches graphically. Now, what I'm going to do in class on Monday is really highlight these, and we're going to spot check a whole lot of them. For example, let's look at number 5, page 25. Now, what is the limit of f of x as x approaches -1 to the left? Yes, that answer is 0. What is the limit of f of x as x approaches -1 to the right? It's again 0. Therefore, the limit of f of x as x approaches -1 itself is equal to 0, because by the definition of limit, the limit of f of x, and I see we need some erasure here. Oh, that's so cute. I didn't know you could erase that well. Sometimes I guess you don't have calibration on this very effectively. I'm trying, gang. I'm trying. I still can't get the calibrated. But anyway, as x approaches -1 on f of x, it's equal to 0 because on both sides of -1 you have the same number. It shows the existence theorem. I don't see anything difficult on 25 for you. I'm looking on 26. I'm getting a little bit bored because of the repetition. But I guess sometimes boredom is good because all we're doing is giving you perfection. That should take the concepts of derivatives of, I'm already in chapter 2 because I've said let's do some shortcuts, but I'll keep to the first section. I'm sorry. That more or less winds it up with what I'm doing in class. Let me say this before I leave you. All these sessions in video I was encouraged to do. However, it doesn't replace you coming to class and being attentive. I will only hit bare facts in every video. There are very few times I will be able to do the proofs without doing them in class. Please consult my website. It's already loaded. I will tell you in class just which ones to pay attention to. They are the syllabus, my web page has everything on it, including the syllabus, your calendar, and all drill sheets to make A's in this course are up for limits already. Have a good night. Nighty night.